First of all, I'd like to thank Ramesh and Quest for giving us the opportunity to talk to you. My name is Vineet, and I'm going to talk about COMSOL multiphysics and how COMSOL can be used for CAE simulations. Before I start talking about COMSOL, can you all see the screen now? Yes. Okay. Not yet. Okay. So before I start talking about COMSOL, I'll talk about the motivation, why analysis and, why multiphysics analysis, specifically speaking. So, I just want to start by highlighting a couple of big incidents, engineering incidents you may have come across over the past 2 or 3 years. The first was the Boeing 787, which is a big, a very big plane and a very popular plane, a big project. And suddenly, there was some thermal runaways in the batteries there. The batteries were catching fire. There was smoke coming out of batteries, and that led to a grounding of all the 787s for about 3 months. That was a big problem. Another thing which you may remember is, the Toyota recall in 2009 or so. What was happening was there was unintended acceleration. So even after the drivers were taking their foot off the pedal, the cars were still accelerating. And the reason for this was actually quite interesting. What was happening was when Toyota moved to their electronic throttle control from mechanical to electronic, what happened is to mimic the tactile response of a spring-loaded throttle, which they earlier had. They added some friction pads below the accelerator. And these friction pads, in some cases, were giving too much resistance. So even when you took your foot off the accelerator wasn't coming back to normal. So it was a very weird problem. And the reason I mentioned these, and there are many more. I mean, you must have heard of Tesla recently. The very popular electric car is bursting into flames and so on. All of these companies are really world-class companies. They make excellent products. We all know Boeing products are great and Toyota is great and so on. Why these these problems? The thing is that we are in a new system today. We have new challenges. We live in a world where product life cycles are shortening. There's a lot of pressure on all companies to deliver newer and more exciting products faster. I mean, cell phones is a great example. Today's model is outdated a year later. So there's a lot of pressure to come up with new technology. And this is what you see, in the case of the 787, it was batteries. And, Boeing was integrating components from thousands of different suppliers into their plane. They were not manufacturing everything themselves. Now, when you have all of these components coming from different suppliers, how are you going to test them? It's very expensive to test them when your product life cycles are shrinking. And that's a challenge which is a new challenge. We didn't have this even maybe 10 or 15 years ago. And of course, cost and quality is always a consideration. We always want to reduce our costs. We keep, as consumers, we keep asking for better quality products and so on. And then, of course, we have global teams. You have geographically distributed teams who have to collaborate and work on products. Or like I said, you have products being sourced or components being sourced from different parts of the world. And then you have to integrate them and you have to test them very quickly. And you have to give warranties and guarantees for tens of years on a product which you may not be able to test for even a year. Apart from that, we have global markets as well today. So you have to sell in different countries, all of which have their own norms and their regulations and so on. So all of these things have to be satisfied. And therefore, when you talk about product design today, new product design, it's no longer good enough to be fast to market, but you have to be smart to market. And that is where simulation can help you. You can optimize or reduce the time that you require to develop a new product. So I'll just discuss a few case studies in the time that I have today. The first is a case study by Toyota. And this is a problem that they had with their new electric cars. They have this Prius hybrid, which has a lot of electronic components in it. And once you have lots of electronics, the obvious challenge you have is heat extraction. There's too much heat generation, and you need to extract that heat. And they were facing a problem there. Oops. Okay. So the design that you see on the left-hand side, this is the cooling plate that they had on top of their electronic control unit. So that is the design that they had. And that was not enough to extract the heat out of the system. They had this problem where it was not extracting the heat. And so what they did was, well, the actual design was they were initially impinging water on top of this, I'll just use the mouse here. So they were impinging water on top of this cooling plate over here, and that was extracting the heat from the system. But as the number of electronic components increased, they were not able to extract that heat. And they tried to do different things. I mean, they tried to increase the pump speed and the power and the speed of the jet and so on, but nothing was enough. And increasing the pump speed led to more power requirements and so on. So they just decided, let's just do away with the design that we currently have and come up with a new design. So the only constraint they had was the outer dimensions of the cooling plate. So they used COMSOL to solve this entire problem simultaneously. So it was a jet impinging on the cooling plate, and they coupled a fluid flow problem with the heat transfer problem, along with topology optimization. And on the left here, on the right side here, you see this is the kind of design they came up with, and they actually manufactured this, and this is what they use as a cooling plate in the Prius today. So I think this is a great example, because how much ever experimentation you do, it's impossible to come up with a non-intuitive design like this, and that is the power that simulation can give you. It can help you come up with efficient solutions for your engineering problems. This is an example of a case study by Boeing, where they have these expanded metal foils. So when you have lightning strikes, you want to absorb the current which comes on the aircraft. And so what happens is, when you have these EMFs, they're very large, of course, and they're covered with a paint. And when there's micro cracks in the paint, what happens is that there's corrosion in the EMF, and that reduces the current carrying capacity of these EMFs. So they wanted to optimize the design of their EMFs. Their objective, of course, was to maximize the current carry and minimize the thermal stresses, because the micro cracking initiates because of the thermal cyclic loading in the aircraft structure. So again, they used COMSOL for this entire analysis. And well, some of the conclusions of the study were that increasing the width of the EMF was preferable to increasing the height. So what they realized is, or what they found from the simulation, is that when they increased the height, there were larger displacements and larger stresses which were induced in the EMF. And increasing the width did not have that much of an effect on the amount of stresses that were induced in the EMF. They also found out, there was a fiberglass layer that is beneath the EMF, and they use this to prevent corrosion, of course, once there's microcracking. But they've realized that once they have this fiberglass layer, it increases the displacement, maximum displacements inside the EMF. And they've also found out that the paint, they paint the EMF with some paint, and the glass transition temperature of that paint also has some influences on the displacements in the EMF. So they need to make sure that the glass transition temperature does not fall within the operating range of the aircraft temperatures, because there's a 60% increase in displacement is what they have found as a result of the study that they have done. And of course, they are working on optimizing this problem right now. A third example that I wanted to share with you was from Siemens. It was a very innovative idea, I thought, so I thought I'll share it with you. And the problem they had was a tire pressure monitoring system. So they have they wanted to design a tire pressure monitoring system. And obviously, because it sits inside the tire, it monitors the pressure in the tire. They wanted it to be wireless, they wanted it to be light, and they wanted it to be rugged, because the warranty on a tire is about 8 or so years. So they wanted a device which would last for 8 years. So they decided, let us come up with a piezoelectric device. A piezoelectric device is, you have this some materials where if you impose some mechanical stresses on them, there's charge accumulation and you can extract that current. So that's a good way, to have a wireless device. So they said, let's have a piezoelectric device. And now of course the challenge was, how do you design it? What should the design be? So they used COMSOL to optimize this, to come up with an optimized design. And they came up with a triangular design for the cantilever, as you can see. They modeled the whole thing. So the piezoelectric problem was modeled in COMSOL. And then they also did a fluid structure interaction, because now, the way you extract electricity is when the cantilever vibrates. And of course, that means you don't want damping in your problem. If you have a very variable oscillation, you will minimize the power that you are extracting. So they wanted a steady, they wanted to minimize damping basically. So did a fluid structure interaction. They solved for the flow problem, the air around the cantilever, and coupled it with the structural deformations within the cantilever to come up with an optimized design for the thickness as well as the shape of the cantilever. And that's one way, that's how they use COMSOL to design this particular problem. So again, all of these examples that I've talked about, whether it's the Toyota example or the Boeing or even the Siemens example, what they wanted to do was design a product. And of course, when you design products, there are different physical phenomena which influence how this product behaves in a real life environment. And that is what they captured using COMSOL. In this case, it was a coupling between a piezoelectric phenomena and fluid structure interaction. Or in Toyota's case, it was optimization, heat transfer, and flow, and so on and so forth. And that is where COMSOL comes into the picture. The traditional approach to modeling has been modeling separate physics individually and then combining them and solving them iteratively. Take information from one physics and feed it to the other, and so on and so forth. But there's a reason for this. When we started modeling way back in the 50s or 60s, we didn't know how to couple physics and solve for them simultaneously. Secondly, we didn't have the numerical methods to solve for them simultaneously, and neither did we have the hardware to solve such large problems. But today, both of these pieces of the puzzle are in there. Hardware is cheap, we have great hardware, and we have the numerical techniques to couple these different physical phenomena and solve for them simultaneously. And that is where COMSOL comes into the picture, because with COMSOL, we give you a graphical user interface where you can couple all of your different physics and solve for it simultaneously. Not only that, if some of you are working on high-end research and you have your own equations, you can enter your own equations in COMSOL within the GUI. You don't have to write any user routines or UDFs. Within the GUI, you can write your equations and couple it with existing physical phenomena. So we provide you a user interface which is very easy to use, and where you, as a user, can choose what physics you want to couple. So there's no predefined constraint on what you can couple. You can choose what physics you want to couple all of them, and COMSOL will solve for all of them simultaneously. Another thing which a lot of people say is, when you are using a simulation software, you also need some insight. You need to understand what you're solving for, and even there, we try to help you as much as possible. So whenever you choose in any predefined physics interface, we show you the equations that you're solving for. We also tell you what terms are going to affect what part of your problem and so on. And if you want, you can modify any of these equations within the user interface itself. Like I said earlier, you don't have to write any UDFs or subroutines to modify anything. Equations can be modified within the user interface. And like I said, you can add your own equations or additional terms to them. You iterate this process till you are happy, and then you move to prototyping. But with a multiphysics enabled tool where you can optimize, like you saw with the Toyota problem earlier, what you can do is you can solve the multiphysics optimized problem to come up with the initial design. Then go to your CAD, do the multiphysics verification, and then go to prototyping. So this should help streamline the product design process that you have. That is what we give you with COMSOL. This is the product suite. So we have this base package, which is COMSOL Multiphysics, which is the graphical user interface I showed you. And all of these physics-based modules are integrated into that graphical user interface. So any of these modules can be coupled with any other module. So like I said, as a user, you choose what physics you want to couple based on the product that you have at hand or the problem that you have at hand today. So we have a lot of physics-based tools like you saw for electromagnetics and structural mechanics and heat transfer, flow, chemical reactions, and so on. And apart from that, we also have some optimization tools, and we have interfacing products where you can connect COMSOL with different kinds of CAD software. So you can shorten your time, the time you take to finish your manufacturing process. So this is what I had to say today. Just a brief introduction to what multiphysics modeling is and how COMSOL can help you do it. Once again, thanks a lot to all of you and to Quest for inviting us here. Thank you.
Are you born to engineer?